Hello and welcome back to Transmission. It's me, Quentin, and this week we're talking all about overhead lines. Now, as a society, we don't really talk about overhead lines very much, but they're everywhere, and they're crucial to how power gets around. And today we're talking to Georg from Gridraven, who have a unique approach to something called dynamic line ratings, which is figuring out how much power you can put through these overhead lines and optimizing that so you can get more out of existing infrastructure. So it's always fun to speak to Georg and really impressed by the business that Gridraven has built. And if you want to find out more, do check them out. We've got some links in the comments. And if you like this conversation or the podcast in general, please make sure to hit like, subscribe, or leave a comment wherever you listen or watch. It really does make a massive difference and increases the impact of all of the content that we produce. So thank you for listening, and let's jump in. Georg, welcome to the podcast.
Thank you, Quentin. It's a pleasure to be here.
And welcome to New York, of course.
Wonderful.
Before we get started, let's just talk about transmission lines, because this will frame the whole conversation. And I think for a lot of our listeners, you maybe notice them when you're driving down the freeway or the motorway and the big pylons and overhead lines, but we don't really think about them very often. A lot of it is actually quite primitive technology, and it's a big bottleneck in getting the energy transition, well, not even energy transition, load growth and electrification, getting that done. So can you just talk to us about overhead lines for a second? What are they? What are they made of? And how do grid operators think about them?
Sure. Transmission and distribution are it's connecting everything we do with the power plants that drive it. There was a wonderful interview by Richard Feynman, a physicist from the US, who described the overhead line as it's basically carrying the amount of a major river in a few wires. You can imagine the transmission line crossing the country as a major river carrying the energy. Like if you would need to put a hydro plant at a city, you would need the entire river, but we can make do. So the transmission lines carry the power on which we grow the world. And it's still the same technology that has been used for over 100 years. It's bare conductors of aluminum reinforced by steel. It's the wires that are hanging freely in the air, exposed to the atmospheric conditions, that we need to build more of to grow the economy in the US and to lift people into a modern lifestyle in many parts of the world.
And so why don't we just build more of them?
That's a great question. We do, and we are investing record amounts of money into building new lines everywhere around the world. The supply chains for transformers, for example, have become long, and like power generators are being ordered. The order books are full. So everyone's building as much as you can. For new transmission lines, you need to have the agreement from hundreds of landowners on the way. Like everybody needs to agree that it's going to cross your land. And as much as I'm a fan of power transmission, even I've had my friends ask me that, hey, George, there's this new transmission line going to be built in my backyard. Should I join the petition against it? And I'm like, please don't. But I totally get you if you don't want that in your land. So that is at core the major reason we can't build new transmission lines in Europe and the US is that we need to have the agreement from lots of people to do so. And it's really difficult to change or make existing rights of way broader for the same reason.
I have actually alluded to your business a couple of times on the podcast before. Big fan of what you're doing at Gridraven, and we're going to talk about that in a second. But the reason why I like it so much is I really like businesses or entrepreneurs that are trying to get more out of existing systems. I like optimization problems. And what you're doing at Gridraven could potentially have a huge impact in reducing the amount of steel we have to put in the air, but also, affecting people's lives who don't want these things in their backyard, the capital that's required. Loads of measurable impact. So can you tell us about the problem that Gridraven solves then, and what's the status quo right now, and how is the way you're doing it different?
Of course. The reason we started the company was we noticed the amount of power plants waiting to connect to the grid. I spoke to solar and wind developers around the world. It's mainly solar and wind batteries that are trying to connect to the grid at the moment. In the US, there's the existing peak capacity of all the power plants in the US today is around 1.3 terawatts. And there's about 2.6 terawatts of power plants waiting to connect, to get a grid connection. So that sort of makes sense because we come from a coal, gas, nuclear-based system where power plants would have had slightly higher capacity factors. I looked this up in the US right now. Coal plants have 40 to 50% capacity factors. That means they're operating half the time. In winter more, 70%, summer less. So when you're going from a thermal-based system to a solar wind storage-based system, you need a bigger grid because now the solar plants have maybe 20% capacity factors. You need twice as much grid. That's one of the big picture issues facing the transmission grid. And the other is that we're trying to grow the consumption of electricity rapidly as industry is electrifying, as we're having new types of industry, as we might even, well, we are definitely electrifying transport. And all of this adds to the demand side. So we're trying to, at the same time, move to a different type of more intermittent energy source and grow the load. So this puts the strain on the transmission lines. As we said, it takes 10 years to build one. It takes maybe 1 or 2 years to build a solar plant, a few years to build a battery. It takes a few years to build an AI data center. So everything else can be built much faster than the transmission line. So that's why it's important that we optimize the existing grid to buy time. It's not about replacing investment into grid. I think we need to build, and we are as a society building huge and record amounts of transmission, and there's lots in planning. But that's going to take until 2035 until we see that. So we don't want to wait until 2035 to develop AI further, for example.
So let's talk about the status quo right now then. How do grid owners and operators figure out how much power, we could do some maths here, but figure out how much power you can put through an overhead line, and what are the inputs to that process?
Sure. So grid operators continually look at what the grid can handle. And the first thing you need to fix is, for these overhead lines that have these conductors, what's the maximum amount of electricity that material can handle? And if you push more electricity through it, it heats up. And so it has a maximum temperature. Now, the actual amount of power that it can transmit also depends on the weather, because if there's a bit of wind blowing on the conductor, it's almost like blowing on your hot soup to cool it down. So it's cooling down the conductor. Even a light wind of 2 meters per second or 6 feet per second adds 1/3 more capacity to a line.
So when we're driving around the motorway or freeway and we see these massive overhead lines held up by pylons and insulators and ceramic things and whatever else, how hot are those lines generally running?
Usually, in normal system operation, we always make sure that if one line goes out has a fault, then the other lines can still carry the electricity flows that will have reconfigured. So this is called the N-1 criterion. So at any one point under normal operation, a power line will not be close to its maximum operating temperature. It will typically be only a few degrees above ambient temperature. So we're not talking about the actual temperature of the lines in normal operation. We're talking about the maximum. It's sort of like the speed limit. And there's an example that's brought that we're operating the grid according to the worst case weather conditions. So basically, you asked how it's set. The physical capacity of the lines varies during a day by 2x. But now, in the absence of precise weather data, you need to make the worst case assumption so that you're safe no matter what. If we take a step back and look at maybe like 60 years ago when most of the grid was built, you had a centralized power plant that was connected with transmission to the city. So you make sure that the transmission has enough capacity to take the peak load. And so you over-dimension the transmission so that even when there's a hot summer day with no wind, it can still handle that transmission. And that excess capacity in the transmission line, that's sort of there, fine, let's be there. But now we've gone from that simple power system model of transmission to consumers, we come to a different type of system where, like, not many people live in the sunniest places in the world, in the deserts or the windiest places of the world. We now have power plants that are really far away from where people live, and so we need much more of transmission to bring the power to where it's needed. So now the additional capacity in the existing grid, that headroom that previously wasn't made use of, is suddenly valuable. It makes sense to unlock that.
And if I remember correctly, back from university days, these overhead lines also expand, don't they? You have sag, if I remember correctly. And so on a hot day, if you've got an overhead line that comes across a freeway or a motorway, you've got to have enough clearance above the top of the truck or lorry, plus some insulator, plus some, I don't know how much water molecules there are in the air or whatever, There's a lot of maths that goes into this. Okay, so the game here is we've got overhead lines. They're really slow to build. We want to get more out of them. And if there's wind or other environmental conditions that vary, then we can change how much power we can put through those lines, right? Is that
Yes, correct.
that's the deal?
You can increase the speed limit, so to say. On the topic of SAG, when I was working at the Estonia's national grid, and there would be an all hands meeting every Monday morning, and so I remember in those all hands meetings, every other week they would describe how somebody was having a construction site under a transmission tower and transmission line, and they would unload the truck to empty it, and it would come like within a meter of the conductor, and if something comes so close to a high voltage line, there will be a flashover from that, and that would cause thankfully almost nobody was almost ever hurt. If the driver is sitting in the truck, then the electricity goes around it. It's like a Faraday cage, but the tires will blow out and there will be an outage on that line.
Not good. Well, however you think about it, not a good day.
No, so high voltage wires are very sensitive equipment that we need to operate very precisely, and if we're now talking about increasing capacity, we have to do that in a very cautious way. So at Gridraven, we have the most accurate weather predictions. I can claim that we have the most accurate wind prediction in the world with machine learning. And what we do is we take into account every part of the landscape, every tree and building and hill that has an impact on wind speeds, because we're trying to estimate what's the maximum capacity of that line. And that depends on the weather conditions, but it doesn't depend on the weather on average. It's specifically in that spot where the transmission line is. You might have a 10-degree difference in the temperature of the conductor within a few tens of yards due to the differences in local wind. So we take that level of detail into account to be able to actually give the grid operators a view of, with 98, 99% certainty, you can push this much more power through.
And it's just like in some European countries where there's two speed limits, one for when it's raining and one for good weather, right? And so how are grid operators doing this right now? Before you and Gridraven came along and said, hey, you know what, we can model this and we can get more out of these existing lines. How are they doing it right now?
Right now in the US, there's a FERC order, 881, that's requiring all transmission owners to take the outside air temperature into account, so that when it's colder, you get maybe 10% more capacity through the lines. So they'll have to account with weather forecast with an hourly resolution to get more capacity out of the grid. So that's great, and they'll have to comply by July this year. Some parts of the US are a bit delayed with that, but it's progressing.
Does it explain how they need to do that, or does it?
Yeah, so what they need to, you can imagine the grid operators have a massive screen where dispatchers sit and look at power plants and power lines, and they will call up power plants to turn things up and down if there's problems in the grid. So on their screen, they will have different numbers for the transmission capacity of a line. We can picture it that way. So they need to have accurate numbers on that to make the right decisions. And that's what FERC Order 881 and also what we help them to do is that we give them the accurate numbers for every transmission line. So it's the speed limit of the grid in a way, so that they can see that, okay, there's additional slack in these lines. If I turn up this power plant here, it's not going to cause any issues. And we're now telling them, like, if you account with the variability during the day, in the next hour, you might actually have twice as much capability. So now if there's a contingency, let's say a power plant failed, they can push even more power through that line and in that way reduce the cost of system operation.
And this is a really sensitive topic, right? Because we're recording this on, what is it? It's almost the end of April. There's just been this massive blackout in Spain and Portugal, all over global news, and ramifications everywhere. I mean, just a nightmare scenario. And there are so many levels of safety, rightly so, put into managing grid infrastructure because it is so fundamental to a working society. So how do you think about applying Gridraven's technology in a sector which is so safety conscious? I'm not going to question whether that's right or wrong, but there might be some tweaking around the edges. How do you think about that? And do you walk into rooms with grid operators and their gut is no, we can't even think about this?
So that's great. I have friends in Spain and Portugal, and it's not fun to be stuck on a train or if everything stops. And it can also be life-threatening, and it's very, very serious. And the most important thing that transmission owners care about is keeping the system running, keep the lights on. So for sure, that's their core task. And when there is an event, when this comes out, we'll probably know what caused the event. Right now, there's a lot of speculation about it, but we know that what happens in blackouts is almost always the same. At some point, something happens in the grid, something trips, something goes offline. Then the next element, the next weakest element, is also reaching its limits, turns offline. It might be a power plant, it might be a line that is taken out of for safety reasons. Power flows reconfigure again and again and again and again. It's a cascade of events that eventually everything stops in the country. And that at some point is what happened. Now there is a role for accurate line ratings in helping prevent those cascades from happening. Quite often, about 80% of the time, dynamic line ratings will give you additional capacity for a line. So you can set the safety limits in those lines at the higher level, so that if an element trips on the line, there's more slack, there's more headroom for the rest of the grid to handle it. It doesn't necessarily have to switch off. That can be one way that accurate ratings help. And the other way that accurate ratings might help prevent things like this, and we don't know whether that was the case in Spain or not, is that under certain conditions, that we mentioned this sagging of lines previously, especially if it's really hot and there's no wind, and you have an outage somewhere in the grid, it's a normal outage, everything's handled nicely, then power flows redistribute as they should. Everything's under the limits that we today have in the grid, but it turns out that some of those limits were too generous. Because we today account with 0.6 meters per second wind in calculating the rating. If there's actually 0, then you'll have 1/3 less capacity, which means that some parts of the network might overheat. And it's also, especially in older transmission lines, there might have been issues with the construction. It's been there for 40 years. Something's been changed, so there's already it's close to the safety limits already. So if it overheats even more, it might physically come too close to a construction truck underneath it. There's a flashover, an unexpected outage in that additional line, and that might have been the straw that breaks the camel's back. So accurate ratings can sometimes also lead to a reduction in the speed limit in the grid. And if you know that a day or two in advance, then you will make sure that the system can handle that and it's not going to cause issues. So having accurate ratings is one of a confluence of things that helps system operators keep things running.
I guess the next frontier beyond this then is, so with dynamic line ratings, is then applying that to dynamic settings on disconnection devices. Circuit breaker, a lot of the triggers for circuit breakers to open are fixed on site. And if we could remotely control those in line with dynamic line ratings, that would be awesome as well.
Well, circuit breakers are usually dimensioned for the maximum, the peak. And the peak happens, 50 hours a year. So if you're not at the peak, you don't actually, for dynamic line ratings, most of the time, you don't need to change the circuit breakers. There's already headroom in there.
Okay.
So most of the time, for DLR, you don't need to. It's possible to do that, but then that's quite a lengthy process, and rightly so.
They're the last resort, right? Load shedding. You kind of don't. You want to get involved with that.
They were really getting into the safety margins. One of the misconceptions about DLR I hear a lot is that people say that it's reducing the safety margin. It's not. We know already today that 1 to 3% of the time there is actually no wind in the grid. So already today we have a safety margin of 97, 98% or something like that. So with DLR we keep that safety margin, or even make it at 99%. So we're more sure that the rating is at least as much. But then when there is wind, we can make use of the additional headroom. And when there's no wind, we have to reduce a bit. So it's taking the safety margin in a smarter way. And also, if you have more slack in the grid, that can actually give you more options for contingencies and avoid blackouts. So I would say that DLR is increasing grid operation safety margins, not decreasing.
So less about safety and more about operability.
Yeah, at the same, it's more about getting the cheapest power to consumers through a bigger grid that we can unlock right away. And the main difference that Gridraven brings to the table, so up until today and for the past 40 years, people have built various types of sensors and physical hardware for DLR. Fundamentally, the issue that needs to be solved is you need to know what the wind and weather conditions are exactly at the span where the cable is. And up until now, the only way to do that was to put a weather device or a sensor onto the wire to measure what's going on. And we're changing that by having the world's most accurate wind forecast with the help of machine learning. one of the things over the last few years, everyone knows the developments in machine learning, and most people follow the developments in solar and batteries. But there's another field of technology that has significantly developed over the last few years, and that's LiDAR. And that's basically using lasers to measure where things are. So 96% of the US has been scanned to within 1 meter from airplanes, and that's public data from USGS. So we know where every tree, building, and hill is, and we're able to predict wind on the entire grid.
Wow. Who did that? Who went and scanned all that?
That's been done by the geological agencies of the states, various states in the US.
Kudos and props to them.
Sure, it's out there and available. So it's thankfully there's machine learning methods to make sense of that huge amount of data, and we can predict wind. I'm moving to Texas in the next few months, planning to, and I like to bring the example there that if it's a windy day and you want to have a barbecue, you can still do that if your house is sheltering your grill from the wind. So the wind is blowing over your roof. And there might be completely no wind where you are. And the same thing with the transmission lines that go through hundreds of miles of country. If even a small part of that is in a forest, then there will be no wind there. And now the weather forecast that we have, that we look on the phone, or that the most accurate on the market, they're giving you the average wind speeds across a wide area, typically about 6 square miles. So that's not sufficiently accurate to tell you what the actual capacity of the lines are. You need to have full resolution, and that's now possible. And that's what Gridraven has innovated.
It's extremely cool. Now, what's the actual impact? So, does this mean we can get a bit more out of these transmission lines, or a lot more out of these? What does that mean in numbers terms?
In one of the projects we're doing, we've seen, it's an old line. So in that line, we've seen an increase of 40% with dynamic line ratings. That's possibly one of the more optimistic or generous ones. In some others, we've seen 10%, 20%. It's not even perhaps so important whether it's 10 or 40%. The most important thing is that, are you sure that it's there? If we're talking about the entire national capacity of the grid, adding 10% is tens of gigawatts of more capacity in the grid. We want to be extremely sure. So we're using machine learning for accounting with the landscape, but we're also giving it the probability estimates of what the winds are. So every prediction we make is with 98, 99% confidence that is really there.
You mentioned it before in our conversation that this isn't about necessarily delaying or reducing grid reinforcement. This is like something different. But surely, if you fast forward 5 years, don't you see a future, an AI or machine learning enabled future, where we're building less stuff because of this?
I think the amount of stuff we want and need to build is outpacing that. So we need to, for the last 2 decades, the transmission industry has been relatively stable. There hasn't been much growth. So we need to build as much and as fast as we can. I think the electricity consumption is going to double in the next decade or something. So we need to build as fast and much as we can. What's going to happen maybe in 10 years' time when we get to, again, a new plateau? Sure, I think at that point we'll not need to build as much anymore, but there will always remain a role for the socially optimal amount of grid that should be built isn't to remove all of congestion. Then you're overbuilding the grid. So some of the congestion will always remain, so the dynamic line ratings will always have a role in that system to optimize it.
Is there a play here for battery owners? Is there something here?
I do think so. The whole reason that the locational marginal prices in the US vary and are not the same is the lack of transmission capacity between the nodes. And now if that transmission capacity is going to vary by 2x in a day, that's going to change the markets. It might also create more flexibility, might reduce flexibility, we don't know. But there's certainly a very good synergy, cooperation between batteries and DLR, that if we get more out of the grid, that helps the power to get where it's needed. If you have storage, that helps the power to be consumed when it's needed. And so these things work really nicely together to power the future.
All right, now it's your chance to plug something. So is there anything you want to tell our listeners that Gridraven's up to or announcing? Of course, you're moving to the US. The US is a big growth market for you, and you're in a few different markets. So is there something you want to tell our audience?
Gridraven is the world's biggest provider of dynamic line ratings by size of grid covered. We're coming to the US, and if you're a utility in the US I want to hear from you. The ability to boost the grid can be done in a matter of months. The time it takes is the IT integration to your existing systems. I'm here to talk about it because the whole reason we started the company is to help lower rates, grow the economy, get more solar and wind into the system. And I would love to accelerate that in the US and contribute to the story here.
Right. Well, we're going to put links in the show notes. And if you're listening to this and you want to get in touch with Gridraven, you should absolutely do it. At Modo, we've been following you guys for a while and been blown away by the business that you've built. So very well done to you. Now for your contrarian view. So I know you've got a few of these. What do you believe that not a lot of other people believe?
When I think of the debates that I often have, also in our company with engineers, power engineers, I would say that I'm definitely on the optimistic side about solar storage and wind-based power systems having more resilience than the incumbent system that we're coming from. Sure, I don't mean that if you just take away nuclear, coal and gas plants and put solar and wind in, that system is going to be resilient. And that's not what I mean. I mean that because we've gone down the route of the lowest energy cost coming from solar and wind because it has zero fuel cost, then we are going to go on this route pretty quickly towards having lots of storage, lots of synchronous compensation, lots of demand response that all together are going to build a more stable and trustable and resilient system than the one we're coming from. I think that's a source of debate. I think most people will say that because of the spinning mass of thermal generators, then we are risking system stability. But I think they're wrong on that.
100%, right? The conventional wisdom is that the old system is spinning stuff is better. I would rather rely on spinning rotors than power electronics.
The future is going to be based on a large number of all connected AI-driven devices that altogether will power our system in a resilient and cheaper way than the incumbent system.
Excellent. Well, Georg, I want to say a massive thank you for joining us on the podcast and coming over to New York to see us. It's always a delight to talk to you. If you're listening to this and you're interested in Gridraven, go check them out. It will be worth your time.
Thank you so much, Quentin. Thanks for having us.